Okay, so we talked about neutron drip line, we talked about alpha decay, we talked about composition of nucleus, number of protons and number of neutrons for having a stable or beta active nuclei and so on. So, today I will take one more example or one more application of this semi empirical mass formula, and that is kind of extrapolation into a very big nucleus. You had seen that for a particular value of z, if you look at how many neutrons can be absorbed in this, then you have some limit after which neutron cannot be absorbed. But there is an object, there are objects in this universe where you have neutrons and neutrons and neutrons only, and these are neutron stars. So, what are neutron stars? What are stars? Stars are big celestial bodies in which the gravitation plays a great role, and stars are formed when all these hydrogen and little bit helium in space that shrinks because of the gravitational attraction, and then somehow the density of core increases, and at the same time the temperature also increases. So, when this mass cloud that collapses at the core because of this gravitational potential energy converted into thermal energy, the temperature increases, the density increases, and at a certain stage the temperatures and densities are so high that nuclear fusion starts, and that it becomes a star. So, you have all those stars in the universe. Sun is our own star from which we are getting all this light and energy and everything to survive. Now, what happens if the star is very big, much bigger than our sun, say 10 times of that or 8 times of that or 6 times of that, very heavy stars. So, there the cycle is it goes from hydrogen to helium. The first reaction in stars is hydrogen goes into helium, 4 hydrogen nuclei, that is 4 protons, they combine and form an alpha particle, protons converting into neutrons and all those things. So, that is going on in our sun. So, hydrogen going to helium. I am not talking much about that, I am only giving a very small introduction to reach this neutron star as quickly as possible. So, hydrogen goes into helium, and then next phase is this helium goes into carbon, then the next phase is carbon, oxygen and neon and other things, and other things, and finally it comes to iron, after which fusion is as such not possible. So, depending on the mass of the star, the things can stop anywhere. In our sun, the thing will stop after this carbon. Okay. But if the mass of the star is much larger than this, then all this can happen, and when at the end the nuclear fusion at the core stops, then the gravitational collapse is too fast. Okay. Because when the nuclear fusion goes on, the energy is radiated outward, and this energy makes some kind of equilibrium between this energy coming out and trying to expand the gas there, the cloud there, and the gravitational attraction which tries to collapse there. So, some kind of equilibrium is maintained, but if the nuclear fusion stops, then this gravitational collapse is much faster, and then you have very hard dense core, and the outer layers which collide on this hard core, they rebound from there, and the star ends its life in what is called supernova explosion. All those outer layers are thrown away into space. But then that dense core which is left, that keeps collapsing, and because of the gravitational attraction, and the pressure builds up too high, the density becomes too high, and its stage comes where all those electrons are forced to combine with protons, and then this proton plus electron making neutrons, that takes place, and most of the protons and electrons, they become neutron and, as you know, neutrino. A neutrino, very quickly they will go out of this star, and what you will have is only this neutron. So, if most of the protons are converted into neutrons by combining with electrons, then you have a star made mostly of neutron. So, almost the entire star, barring a some small surface layer, is made of neutrons, 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 neutrons only. Of course, there are very interesting properties. This neutron star, once it is in this format, it rotates very at a large spin velocity and all those things. So, that maybe we will talk about that later, but here the idea is to tell that there are bodies in our universe where unstable, where you have mostly neutrons only. So, mostly you have neutrons only. How many neutrons you think it would be here? Once it is a neutron star, the mass is, say, of the order of the mass of the sun, or little larger than that, 1 or 2 masses, solar masses. Okay. So, this could be something like 1 to 2 mass of the sun, and the radius could be few tens of kilometers, say 10-20 kilometers, depending on which kind of star it is. So, in about 10-20 kilometers of radius, the mass much more than solar mass, that is combined, compacted. So, how many neutrons will be there? If the mass is mass of the sun, how many neutrons you think would be here? So, that could be a really very, very large number, and this object of so many neutrons is also stable. Okay. We had talked about the stability. So, these many neutrons compacted in a small volume, small in the sense that the number of neutrons which are here and the mass which is here, in that comparison it is small, it is still 10-20 kilometers radius. So, we had been talking of nuclei of the radius 4 femtometers and 5 femtometers and 2 femtometers and so on, and number of nucleons 100, 200, 50, 60, 10. So, these we were talking of, but here we are talking of a large, much larger number of neutrons. If you calculate how many neutrons will be there, if it is one solar mass, the neutrons making one solar mass. So, that number will come out to be something like 10 to the power 55 or so. So, on earth we do not see a nucleus of 2 neutrons, right. Even a nucleus of 2 neutrons will be unstable, 3 neutrons, 5 neutrons will be unstable. You need protons, together with protons you have neutrons, and then you make the nucleus. For a particular value of z, there is a fixed number of neutrons which can get into it, and after that it drips, neutron drip line that we talked yesterday. And here with no proton in the core, barring some surface layer where there can be something, some protons or some other nuclei, the whole of this big mass is made of neutrons only and is stable. So, how do I understand this? If 2 neutrons cannot make a nucleus, and you do need proton to make a nucleus, okay, what stops having too many neutrons and too few protons at asymmetry energy? N minus z whole square, that term, that increases the mass energy, and the binding energy will become negative. So, but here you have a case in our space where you have such a big nucleus, and the clue is the gravitation. The neutron star is formed from gravitation only. This kind of extraordinary density is resulting from gravitation only. This these many neutrons, some 10 to the power 55, 56 neutrons, they are packed into a volume of few kilometers, whereas if you look at the sun, it is thousands times much more bigger size. That is because of gravitation. So, gravitation is playing a big role, and if gravitation is playing a big role, maybe we have to consider, when we consider binding energy, we have to consider gravitational potential energy also. Okay. In our discussion, we took care of Coulomb potential energy. We are taking care of these nuclear interactions, potential energy coming from there, binding energy coming from there, that is AV times A and so on. So, all those things we are taking care of, but we are not looking at the gravitational attraction between the protons and neutrons. That is because at that smaller scale where we have nuclei commonly found on earth, the gravitational attraction is much smaller, absolutely negligible as compared to the nuclear in femtometer size, in femtometer distances, nuclear forces are much more effective than gravitational force. So, we altogether we did not see towards gravitational attraction when we were discussing these nuclei. But these kinds of objects, neutron stars, where the gravitation is so important, then gravitational potential energy should also be taken into account. That is one. Now, the question is, the values or this model of semi empirical mass formula that is derived on the basis of observation of this terrestrial nuclei. AV is equal to 15.5 MeV, or AC is equal to 0.72 MeV. All those numbers and even this structure of semi empirical mass formula, that is derived from the observations of nuclei that we find on earth or we find in our laboratories. Now, can this be extended to objects like neutron star after taking account of gravitational potential energy? Of course. Will the structure of the formula and will the values of those parameters which are obtained from these nuclei, commonly seen nuclei, will the same structure and will the same parameters be applicable for an object where you have 10 to the power 55 or 56 neutrons? So, let us do it and see what happens. Okay. So, I write the semi empirical mass formula together with gravitational potential energy. How much will be gravitational potential energy? That also we can work out. You must have done in your school, if you have a mass in a sphere and assume uniformly dense sphere, total mass capital M and total net radius r. So, what will be gravitational potential energy of this object? So, it is simple to derive. You take the density to be rho, and rho will be m divided by pi r cube. This will be the density. We are talking of just mass density, mass per unit volume. Construct this sphere layer by layer, right. So, from infinity you bring masses, pieces of masses, small pieces of masses, and then construct this sphere. That is how you calculate potential energy. Similar is the story when you calculate potential energy of a uniformly charged sphere. So, when the radius is a small r, that time you bring masses from infinity and put put that mass here. So, that radius becomes r plus dr, and see how much is the work done in bringing that mass from infinity and putting it here. Right. And so, that is easy to calculate. Calculate the potential of this object, this sphere here at the surface, and then multiply that potential by the mass that you are bringing, that is the potential energy of that particular layer. Okay. So, that gravitational potential energy that you can calculate if the mass already accumulated here is small m, radius small r, then next layer that you are bringing will have a mass 4 pi r square dr times rho, where the radius is increased by dr, and already accumulated mass that will have a potential g m by r equal to this. Negative of that sign we will take care. So, the work done that you are doing bringing this layer from infinity to here will be this potential times this mass that you are bringing, which will be g 4 by 3 pi r square rho and times this 4 pi r square dr times rho. So, this is g 4 by 3 pi here, this 4 by 3 pi, r square into r square will be r 4. Okay. And then what is left? What is left? So, we have taken this g, we have taken this 4 by 3 pi, we have taken this r square, we have taken this r square, this 4 pi will be there, correct. So, 4 pi and rho square dr, that is g, take 3 here, this is 4 pi square, and rho square is total mass, rho is total mass square and divided by total volume, that is 4 by 3 pi capital R cube, this is the total volume whole square dr. And where is that R 4? Here is that R 4. Okay. So, this will be equal to g by 3, this 4 pi square and this 4 pi square goes away, and this 3 square here will be 9, 1 by 9. So, 1 by 3. So, this 3 will go up. So, 3 goes up. Okay. So, this 3 goes, so this 3 cancels and this 3 goes up. So, let me write it 3 g. So, this we have taken, this we have taken, this we have taken, 4 pi square and 4 pi square they cancel out, and then what is left? M square small r 5 by 5, small r 5 by I am integrating now, okay, integrate it, r 5 by 5 from 0 to capital R, and in the denominator r to the power 6. Check, I have integrated. So, this r square r 4 dr, that has become r 5 by 5. So, r 4 dr is taken care of, m square is taken care of, and other things are all taken care of, correct. So, this is 3 by 5, this is 5 capital G m square by r. So, this is that gravitational binding energy, right. Gravitational, because of this gravitational attraction, this is the kind of energy that is resulting. If you are looking for the potential energy, it is negative of that. From all pieces at infinity, when you combine it into one mass, then because of this attraction, the total potential energy is going down, the total mass is going down, binding energy is going up. So, this term will be added to binding energy. So, if I take this gravitational binding energy in the total energy of the nucleus, we had not done so far, because we were talking of tiny nuclei, carbon and oxygen and uranium and iron and zinc, and these are tiny nuclei. The radius was in femtometers, 3-4 femtometers. So, at that length scale, the gravitational forces are totally negligible as compared to the nuclear forces. So, gravitational binding energy we had never considered, but now that we are talking of neutron star and this and that, where it is the gravitational attraction that is playing the key role. So, we will write our mass formula once again, assuming that it is it can be applied to those big masses, because this mass formula was derived on the basis of observations of these commonly available nuclei on earth. So, just assuming that this can be extended to this systems like neutron stars and so on. So, our mass formula should be modified to binding energy AV times A minus AS times A to the power 2 by 3 minus, you speak loudly, minus AC times ZZ minus 1 upon A power 1 by 3 minus asymmetric n minus Z whole square by A plus delta. This was these 5 terms were there. So far we had considered this, and now you add this plus or minus plus, because it is adding to binding energy. It is adding to binding, it is attraction, it is providing you binding energy. So, plus 3 capital G m square over 5 r. Okay. We can write this term in terms of capital A and so on, this last term here 3 G m square by 5 r. In fact, let me do that. So, this will be 3 G, m will be mass of neutron times A, and r will be r naught A power 1 by 3. We are now talking of neutron stars. Okay. This is for neutron star. So, all the nucleons are neutrons. So, mass of that neutron star is mass of all those neutrons, a mass of one neutron is this Mn, and there are capital A neutrons. I am not going into the detailed structure of neutron star. I am just taking it as a just neutrons, neutrons, neutrons making this whole body. Once you go for neutron star physics, you will have more detailed structures. The core is neutrons, but then you can have on the surface some other nuclei floating here and there. But take it as a just a neutron, only neutron, a star of only neutrons. So, there are capital A nucleons, all neutrons, and therefore, mass capital M is Mn times A. So, square of that. Radius of a nucleus is r naught A to the power 1 by 3. What is r naught? 1.2 femtometers. Once again, this 1.2 femtometers times capital A to the power 1 by 3, that is that we obtained from measurement of radii of the commonly available nuclei, right. The radius was measured using electron scattering or other experiments on those nuclei, and from there we had derived that radius goes as something like 1.2 femtometers times capital A 1 by 3. So, I am just taking this formula to neutron stars. We do not know whether it is valid there or not, but just let us take it there. Whatever we have seen for this commonly available small nuclei, we just assume that let us apply it there and see what happens. Okay. Justification will come if there is some agreement. So, I am writing this as this. So, this term will be, so let me in the next line we will add that. So, AV times A, now look at this second term. This is proportional to A to the power 2 by 3, it is surface term. It is surface term, and you know, as you increase the volume, the contribution from surface goes down in proportion to the contribution from the volume. Okay. If you increase the total mass, total volume, then surface also increases, surface area also increases. If you think of a sphere and you increase the volume, then what will you do? You will increase the radius, and once you increase the radius, surface area also increases. So, any contribution from surface will also increase, but then volume increases in proportion to radius cube, whereas surface increases, surface area increases in proportion to r square. So, as this r gets larger and larger, the increase in contribution from volume will be much more than increase in the contribution from the surface. So, the importance of surface will go down as you increase the size of the object, although the surface is increasing, but in proportion to volume, the contribution from surface in proportion to volume, that importance will keep going down. On the other side, if you decrease the volume of your object, then the surface becomes more and more important. That is why nanoparticles, nanomaterials have a very different property set than the bulk materials, because the particle size is very small. So, as the particle size gets smaller, the contribution from those surface particles sitting on the surface, that becomes dominant. So, in usual bulk material, the properties are decided more by those volume interactions, the particles which are in the volume, they decide the properties, but in nanoparticles is the surface which decides the properties, and therefore, you have a new class of materials with new properties with which you can manufacture newer things, you can do a totally new physics. So, this surface term let us neglect as compared to the volume term, because the object is likely to be very, very large. So, this we will neglect. This is coming from Coulomb potential energy, interaction between protons. If there are no protons, so this also we neglect. This one is minus asymmetry n minus z square. There are no protons, this is capital N square, but then capital N is same as capital A, right. If there are no protons, then the number of nucleons is same as number of neutrons. So, capital N is same as capital A, or you also remember we wrote it capital A minus 2z whole square. So, if z is 0, so capital A square here and A here. So, this is A. This pairing is also we are going to neglect. This is coming from even number of nucleons and odd number of nucleons. So, if you are likely to have some 10 to the power 50, 54, 55, 56 nucleons, so one more or one less is not going to change the energy of the system by any significant account. So, this also we can neglect, or you can also think in terms of it is some constant divided by capital A to the power 3 by 4, and capital A is so large. So, forget this also. Then comes this plus this one, let us write from here, this is 3 g mn square by 5 r naught a to the power 5 by 3. Okay. Now, this is binding energy, neglecting those relevant terms and keeping these terms and including the gravitation. Now, for a system to be bound, binding energy should be positive, right, because binding energy is difference between total mass energy when the whole thing are separated, the parts are separated from each other, all nucleons separated from each other, then the mass is larger, and the bound system mass is small, that is why it is bound system, mass is smaller, and that difference is binding energy. So, this binding energy has to be positive, then it is bound. So, you can have a nucleus of only neutrons provided this binding energy is positive, right. We are writing these expressions assuming that I have a nucleus with only neutrons, and now we are we have written an expression for binding energy. If this binding energy turns out to be positive, yes, I can have that. So, let us see in what condition this will become positive. So, for this neutron to exist, neutron, the only nucleus of only neutron to exist, binding energy should be greater than 0 or say equal to 0. So, that means A V minus A sim capital A and plus 3 G m n square 5 r naught A, this should be greater than or equal to 0. I can divide by capital A. So, it is A V minus A sim plus 3 G m n square 5 r naught A power 2 by 3 should be greater than or equal to 0. Let us put the values. How much is A V? 15.5 MeV, and how much is this A sim? 23 MeV plus 3 into G. Next line I will write the values. Okay, let me write G m n square by 5 r naught A 2 by 3 greater than 0. Now, from here itself you can see, if you do not have this gravitation coming here, if you do not have this gravitational term coming here, this will not be greater than or equal to 0. It is 15.5 and minus 23, right, this is negative. So, without gravitation you will not have that nucleus of only neutrons, right, but once this gravitation is there, positive term is there, it is possible. So, this equation is 3 G m n square by 5 r naught A power 2 by 3 should be greater than or equal to, I am taking it to the other side. So, it is 23 minus 15.5, how much it is? Minus 7.5. 7.5. So, this is 7.5. Remember the units, or A 2 by 3 should be greater than equal to 7.5 MeV times 5 r naught divided by 3 G m n square, right. A 2 by 3 should be greater than or equal to 5 by 7.5 MeV multiplied by this 5 r naught and divided by 3 G m n square. Now, let me put more numbers. So, this side is 7.5. Let me do everything in SI units. We have to put this capital G, which I know in SI units better. So, let us do everything in SI unit. So, mega electron volts, here is mega capital M 10 to the power 6 and electron volt. 1 electron volt is how many joules? 19 joules. So, I am writing everything in SI units. So, 7.5 MeV I have written into 5 times R naught, capital R naught. How much is capital R naught? 1.2 femtometer. So, minus 15, okay, divided by 3 into capital G 6.67 into 10 to the power minus 11 into mass of neutron in kilograms. How much is this? 1.67 minus 27 kg n square, and this should be unitless. This is coming capital A to the power 2 by 3 that we are doing. So, if I have written everything correctly in SI units, all those units will cancel out and you will get just a number. Let me work out it little bit further. 7.5, 1.6, 5, 1.2 into 10 to the power numerator. Look at the exponent, how much it is? 6 and minus 19, that is minus 13, minus 13 and minus 15, minus 28, and this side 3 into 6.67 into 1.67 into 1.67, and then you have 10 to the power minus 11 from here and 54 from here. So, minus 65, right. So, this will be some number, it is not going to affect much. This side 7.5 into 1 point, this will be around 10, 50. So, this side will be around 50 or 60 or so, and this is also like that. So, this will be some number around say 1 to 10 or something like that, 10 to the power. So, this is of the order of 10 to the power minus 28 and plus 65. How much it is? 37, and this is, remember, capital A to the power 2 by 3. So, capital A should be greater than 10 to the power 37. I am writing the order of magnitudes, right. 10 to the power 37 to the power 3 by 2. This is 10 to the power 37 and multiplied by 10 to the power, how much I had? 19. This is 10 power 37 multiplied by square root of 10 to the power 37, and something is coming from this side also, and I can see it is more than 1. So, it should have been 18.5 if I take square root of this, but then this factor also an order of magnitude calculation. So, it is this. How much it is? 10 to the power 'So, you cannot have a nucleus of 2 neutrons, you cannot have a nucleus of 4 neutrons, you cannot have a nucleus of 10 neutrons, you cannot have a nucleus of 100 neutrons, but you can have a nucleus of 10 to the power 56 neutrons. Now, let us say in terms of mass, kilograms, how much it is? Mass for this number, this is, it should be greater than this, right. A should be greater than this. If this is the number of neutrons, what will be the mass? Mass will be equal to 10 to the power 56 and mass of a neutron, kg. How much is this? 10 to the power 29, okay, 10 to the power 29. The mass of the sun is around 10 to the power 30 kg. Mass of the sun is around 10 to the power 30 kg. So, you see, it is giving you the right order. Neutron stars are observed or are known with masses somewhat larger than mass of the sun, 1 solar mass or 1.5 solar mass or 2 solar mass. This is the order of neutron star masses that are actually observed, and it says that mass should be greater than 10 to the power 29 kg. So, it is hitting the right order, right. So, the semi empirical mass formula which we worked with or which we wrote, making observations on tiny nuclei and taking all those models and those things, that can be extended to these objects, these celestial objects where very large masses are involved, and the calculations with the same number that we derived for this common nuclei are not too bad. Okay, they are not too bad, they are giving me the right kind of order of magnitude. It is not that this is totally failure, it is giving me that a neutron star can exist with 10 to the power 20 neutrons, it is not giving that, or you need 10 to the power 70 neutrons minimum. No, it is giving the right kind of order. Now, this particular example has been worked out in a book. I have taken, it is from this book. It is called Basic Ideas and Concepts in Basic Ideas and Concepts in Nuclear Physics, right? In Nuclear Physics by Haid. And it is published by Institute of Physics Publishing. Okay. So, that is all I wanted to talk about this semi empirical mass formula. Remember, I recapitulate things. This we wrote using two different varieties of modeling. One where nucleus was taken as a liquid drop. The kind of terminology we use for liquid drop, that we are using here. The volume, the surface, and the interaction, Coulomb interaction. So, it is a charged drop. So, in a liquid drop, the interaction between molecules is also short range, because molecules are electrically neutral. Okay. So, and the interaction between molecules is coming from electromagnetic interaction only. So, if it is neutral, if you have two neutral objects, then there is no Coulomb force as such. But then if they are very close to each other, so that it is not really charge 0, the total charge is 0, but the charge is distributed plus and minus inside the molecule. If the two molecules are close to each other, they see this structure, and from there the interaction occurs. If the molecules are slightly apart, then they are neutral particles, and they do not see much of the charge distribution, and the force is 0. So, at that scale, the molecular forces can also be treated as short range, and therefore, the binding energy is proportional to volume and then surface and all those things. So, the nucleus is treated as a liquid. So, that is called liquid drop model of the nucleus. Okay. So, the first three terms in that semi empirical mass formula are essentially treating nucleus as a liquid drop, whereas the other two terms, there it is more like quantum mechanical energy levels and Pauli exclusion principles, and two neutrons should not have same quantum number, and this and that, all those things. So, that is those energy levels coming in discrete energy levels and nucleons filling all those things, and then the coupling, pairing, where the angular momenta are coupling to in a particular way, spin and all those things. So, this is the model which we call nuclear shell model. So, the semi empirical mass formula is kind of combination of nuclear shell model and liquid drop model, okay. And from there we derive this mass energy or binding energy, and from there many of the observed properties of nucleus can be explained rightly, as you have seen, the stability against beta decay, the mass parabola, existence of one stable isobar or two stable isobars, even a nucleus, odd a nucleus, alpha particle stability, neutron drip line, many things, fission, right, fission. So, heavier nuclei will be unstable against fission. So, many of these energy related properties of nucleus can be very nicely understood with semi empirical mass formula, and just now as I had said that it can even be extended for those astrophysical objects where the numbers are very very large. There also this formula with the same numbers is not that bad. Okay. So, that is all about this, and the next topic that I will take in next lecture will be on we are going towards nuclear shell model, but first we will discuss the nuclear interactions between two nucleons, just two nucleons, and those the two nucleons, a nucleus with two nucleons is deuteron, and we will study little bit about deuteron, just this two nucleon system, and then we will move to nuclear shell model. Okay.